This video will explain the progress that I've made in a computer science PhD from Florida Atlantic University during the fall 2021 semester. This video will describe published papers, papers that are currently under review, as well as papers that are in progress for future publication and future research in my PhD at Florida Atlantic University. The first paper I published in the fall 2021 semester was investigating the generalization of image classifiers with augmented test sets. This paper was published and presented in the IEEE ICT AI Conference 2021. The core question motivating this paper is, do the inductive biases in data augmentation complement the inductive biases in neural architectures? Particularly, we define these biases as global and local spatial biases in computer vision. So for example, the convolutional neural network architecture uses a local bias by having a translation invariance built into the convolutional kernel, which is how it processes inputs and maps them to outputs in the neural network architecture, compared to the attention neural network, which uses a global bias. So the global bias is attending over processing the entire input image at once, whereas the local bias only processes usually 3x3 windows at a time. We tried to see if these global or local biases in neural network architecture, the convolution or the attention layer, match the biases in data augmentation with respect to global and local positional biases. So for example, in data augmentation, we can use translation augmentations to slightly shift the pixels left or right, up or down, similar to the convolutional invariance bias. So we test whether these biases come out on the other side with respect to if you use a convolutional network and then test on a data set constructed with translations compared to cutout, which is a more global bias, and we see whether we can understand the relationship between two kinds of prior knowledge kind of interfaces for these artificial intelligence systems based on deep learning. Our findings is that we know less than we think about how priors interact with each other in deep learning systems. Even though we may be able to understand one prior knowledge idea isolated by itself, once they start to interact and you have the global and local bias in architecture as well as the global and local bias in augmentation, you can no longer really predict what's going to happen as these biases interact with each other in these highly complex deep learning systems. The findings from investigating the generalization of image classifiers with augmented test sets inspired future work into multi-distribution learning, and this submission was unfortunately rejected from ICLR 2022, but we received great reviews and plan to continue developing this research. The idea is inspired by, instead of doing train test splits of the data, we do train test splits of data augmentation. So it's encountering augmentations in the test set that it hasn't seen in the training set. So for example, if it trains with the translation and cropping augmentation and then is evaluated on the rotation augmentation or the brightness augmentation applied to the same testing data set. So the core question we tried to answer with this paper is, how many training augmentations can we learn with one model? And we found interestingly that we can't learn many of these augmentations with one model. So for example, if you train on an augmentation then test with that same augmentation, it's no longer a novel test distribution, so it will perform pretty well on this test set that's already seen in the training set. So we tried to see how many of these we could cover with standard training without any kind of extra multitask learning ideas with one model. So this inspired us to do a multitask grouping analysis where we found which augmentations train better together. So we can group together augmentations that are able to optimize each other simultaneously, compared to whereas just trying to randomly sample augmentations to cluster together in training doesn't work very well. We further submitted a paper to the CVPR 2022 conference based on these findings and the future work that it inspired. So we found that standard supervised learning looks limited with learning invariance to many different kinds of data augmentations, whereas we define them as augmented distribution shifts. So instead of doing standard supervised learning, we look to doing consistency learning. So basically you reformulate the task from comparing predictions with one-hot encoded labels to predictions on different augmentations and trying to have it be consistent with its prediction for different data augmentations. We proposed a novel distributional distance metric in order to probe for the invariance that is learned in these models. So what we do is we compute vector representations of the images for both of the distributions, and then we calculate the vector distance between these two vectorized data distributions, and we try to minimize that distance when we know that it's a label preserving transformation. So for example, we want an image and then its rand augment or some augmented counterpart like a rotated image to have a similar prediction compared to any other kind of image in the batch. So our finding is that we achieved a massive decrease in distributional distance as well as a nice increase in the original accuracy as well by using the consistency learning loss to really particularly emphasize learning invariance to label preserving transformations of the data. We've also published Keras-BERT, modeling the Keras language, and this paper is published and will be presented in ICMLA 2021. This paper was inspired by work I did in the spring 2021 semester on text data augmentation, seeing how we could apply techniques from image data augmentation into the text domain. This inspired me to develop a project in the text domain and natural language processing domain so that I could have more intuition for how to apply the data augmentation and have more of an environment to test these ideas in. So this idea, the primary contribution was constructing a novel data set. I went and found a bunch of information about Keros on the internet and annotated this data, labeled it, and made it accessible. So I trained a language model on this data set and evaluated how well it can perform with basic question answering and database completion, which is known as closed tests, where you mask out one of the words, and it's similar to the training task as it tries to predict what the masked out word was. I compared this with fine-tuning from natural language, finding that this didn't work very well, and then I compared it with zero-shot inference from a very large model, the GPT 6 billion parameter model, which is an open source checkpoint of this kind of architecture, and found that the very large model did perform extremely well and much better than the current state of Keros-BERT. So our findings overall were that Keros-BERT has a strong sense of the Keros vocabulary, but it's not flexible enough yet to really perform question answering with any kind of question you might have about the Keros programming framework for deep learning code. These are some of the projects that have been worked on in the fall 2021 semester that haven't yet been published but are nearing publication very soon or submission very soon. The first of which is bootstrapping Keros contrastive annotations targeting the NAACL Conference of Natural Language Processing. This is where labeling the data for Keros code examples to find nearest kind of code example, labeling them based on semantic similarity, such that you can bootstrap a data set and start to do semi-supervised label propagation with the contrastive annotations. The second of which is invariance teaching networks. This is where we use the same kind of distributional distance metric in order to guide the generation of a generative teaching network. And a lot of this is too high level to just describe quickly, but it's the idea of trying to generate a data set and have meta gradients where you have outer inner loop optimization that still uses gradient descent and this kind of learning algorithm. The third of which is the MHS dataset. We've worked with the Memorial Healthcare System to access their dataset through a thin client layer where we have uploaded our Python libraries and we're developing on the FAU VMware machine. The first of which is patient outcome time series modeling. We have a time series sequence of the severity of respiratory illness for COVID-19 patients, and we're looking to model out and roll out the time series of the progression of the severity of the illness using the additional tabular features, as well as particularly the responses to different kinds of therapies like the convalescent plasma and these kinds of ideas that are abstracted in the tabular data set. The next project of which is contrastive learning for patient retrieval, where we want to form vector embeddings of patients such that we can find near similar patients. We're firstly looking for similar patients within the MHS dataset itself, within the same hospital system, but then also we're connecting this to the COVID-19 literature, which is a collection of COVID-19 clinical trials, patient care across the world. So we're connecting the patients with the body of scientific literature and trying to see if we can find relevant information for each patient by using the vector encodings of their characteristics, like how they're responding to these different kinds of therapies, and connecting this with the overall literature on these therapies and generally what's happening in clinical trials. So with that said, my dissertation topic is currently aimed towards data augmentation and deep learning, the first chapter of which is based on describing the different augmentations that have been used, as well as the strategies for how we're using data augmentation. I've heavily explored consistency training, which is a very interesting idea of explicitly using a loss function to encourage invariance to these augmentations, as well as looking at contrastive learning, and particularly in the text domain, determining whether augmentation is the best strategy for forming similar pairs or if it will require manual labeling. So this is the current status of my PhD progress and what was achieved in the fall 2021 semester. Really looking forward to developing these projects further in the spring 2022 semester and exploring the topic of data augmentation in deep learning. Thanks for your time and listening to this presentation.